In this video, I'm going to try to explain, generally and with a few examples, how to analyze dynamics problems that involve interacting objects. So it could be two boxes with a string between them in tension, or it could be two boxes pushing on each other, and there's a Newton's third law pair between them. We'll go over the generals and a few specific examples. The generals fall into two steps every single time you do this. The first one is to analyze the entire system, and the second is to analyze the individual parts. And when you analyze the system, you will gain a piece of information from that. So in analyzing the system, you'll be able to figure out the net force of the system, the mass of the system, and the acceleration of the system. Since these objects are interacting, the acceleration of the system and the acceleration of the part are going to be the same. That's going to allow us to solve information about the parts of the system, knowing that those two numbers are going to be the same. So the parts that we would be interested in are the net force on a part, the mass of that part, and the acceleration of that part. The link between these is that if they're attached to each other, however one is accelerating, all of them are accelerating the same. Let's look at a simple example of this. So you will sometimes see a problem in which you have two objects, call them object A and object B, being pushed by a hand or something else. There are some things we know about this. If A is accelerating, then B has to be accelerating the same because they're attached to each other. We also know that there is a force that occurs in between these two, which is a Newton's third law force. A will push on B, which will get B to move, but B is also going to push back on A, eliminating some of the force that the hand is putting on A. So let's put some numbers to this. Let's say that this hand is pushing with a force of 6 newtons. That's a hand, by the way. Pushing with a force of 6 newtons on block A and block B. And I asked you how much force does A exert on B? And since that's a third law pair, A pushes on B, B pushes on A, I could ask you equally how much force does B exert on A, and you should get the same answer. There's one missing piece of information here. If I push with 6 newtons, we need to know how much mass that I am pushing. So let's say that A has a mass of 2 kilograms and B has a mass of 1 kilogram. What we're going to do is the general steps I outlined before. Look at the system as a whole, and then look at the individual parts. So, system as a whole. If we drew a box around this, we have A and B, and we're assuming here no friction. If we look at the entire system, everything inside of this box, then there's an interaction between A and B, but that interaction does not affect the whole system. The only force that we really care about is going to be the 6 newtons that I'm pushing on the entire thing. There will also be a force of gravity and a normal force, but since those are equal, they'll cancel each other out. So just 6 newtons. So for the whole system, system. The net force is 6 newtons. The mass of the system is the 2 kilograms of A and the 1 kilogram of B, so 3 kilograms. And we want to know the other piece. So all we can figure out is F, M, or A. The acceleration of the system will be net force divided by mass, 6 divided by 3, or 2 meters per second squared. Once we have that bit of information from the system, we can look at an individual part. So let's look at part A. We know that the acceleration of A is 2 meters per second squared, because the system is all of the parts. They all have to be accelerating the same. We know that the mass of A is 2 kilograms, so we can figure out the net force on block A. Simply m times A, Newton's second law, which gives us 4 newtons. We could also look at part B. The acceleration of B, being part of this system, is the same as every other part of the system, 2 meters per second squared. The mass of B is just 1 kilogram, and so the net force is MA. That's 2 times 1, or 2 newtons. Now this tells us the net force on A and the net force on B, but my question was, what is the force between A and B? So to figure that out, we need to now look at the individual free body diagrams of the two boxes. Box A has a force of 6 newtons on it, and another force, the force of B pushing on A, that we don't know. But we do know that these two forces have to add up to 4 newtons. If we look on the free body diagram of B, my hand is not touching it. The only thing touching it is the force of A on B. Now we already know that the net force is 2 newtons. So if that is the only force, then the force of A on B has to be 2 newtons. We can check if this makes sense by going back to the other side. If the force of A on B is the same as B on A, then this must be 2 newtons. And if I have 6 newtons pushing to the right and 2 newtons pushing to the left, my net force will be 4 newtons, as I predicted before. Now I simplified when I drew the free body diagrams. I could have included the weights and normal forces on each of those, but as we've seen before, for solving problems I can eliminate those to just make things a little bit faster.